Hello everyone. So as you understood, today we'll talk about Unicode security and give you an overview of the attacks we can do with that is due to Unicode unique and complex mechanisms. So I'm Alexander. I come from France. I'm a pen tester at Synactive and also a maintainer of Black Arch Linux. I will give you a quick introduction of Unicode, what it is and how it works, so you can well understand what I will show when I will talk about security of those mechanisms later. So to make it short, Unicode is one encoding standard to rule them all. It tends to unify all the old encoding standards because there was one for each region, for each language, for each systems. So there was quite a lot of them, and it was quite complex to convert from one to another. So Unicode tends to solve that. In Unicode, you will find thousands and millions of characters. Not only the letters from all the common languages, but also some punctuation, symbols, emojis, and any kind of shapes and stuff. Unicode works like a software, so it has version and it's growing over time. So every year, new characters are added over time. So for the vocabulary, I will often talk about code points. So you can see Unicode code points as a unique identifier of a character. It's often written as an integer or as an hexadecimal value. So the standard way to write them is an uppercase U followed by the hexadecimal value of the code point. I won't enter into the details of how the encodings are working, and I will mostly focus on UTF-8, but just so you know that when we are talking about Unicodes encodings, a character can be encoded into a variable length. So, for example, for UTF-8, it can be 1 byte up to 4 bytes. There are some unique mechanisms like composing. You can have, for example, the encode accent as a pre-composed character, so just one character, but you can write it in other way, such a normal E followed with another cute accent and compose them together. So they give the same result, but they are not the same. So this will bring some challenges. There are other mechanisms like joining. To extend the number of possibilities, as you saw in the chart earlier, there is about 160,000 characters, but with joining, you can bring that up to 4 million characters by joining them together. For example, there are control characters like variation selectors, so you can take a hand, give it a color variation selector and get a hand with another skin color. Or you can take an emoji, for example, the heart emoji, join it with a fire emoji, and you'll get the heart and fire emoji. I think you get it. So now let's talk about security. So typically, the security issues in Unicode you will face in software will come from the complexity of Unicode on many dozens of complex mechanisms that we'll see some of them during the presentation, and the lack of awareness from developers that there is stuff to manage with the encoding, the complexity of those mechanisms, and so it will lead to implementation error, of course. So to begin, the most easy to understand attacks are maybe the visual one. So we'll have issue with homoglyphs. What are homoglyphs? They are characters like look very like one another, but are indeed different. Of course, it will depend on the font you used. So as an example, on the left, in blue, you have a normal small case Latin letter A. And in red, nearly perfectly the same, but just a bit different. You will get a mathematical symbol A that looks a lot like it, but it's not exactly like it. So this kind of visual confusion will be used by attackers, for example, in phishing attacks. For example, it was used a lot as a something that looks like typo squatting in domain names. So user will think he is reaching the legitimate website, but it's not. And a lot of font-specific attacks I won't talk about, and I will just give you right now an example of source code backdooring you can do with homoglyphs. So if we quickly take a look at this JavaScript code, we have something like a web server with two environments possible. Right now, the server is running the production environment. And you see there is a isAdministrator function that is looking for the current environment. And there will be like a bypass check if the environment is something else than production. So as we are running production, you are expecting that the return value is false. But what you thought in the condition was an exclamation mark for the negation operator was not it. It was actually retroflex click character that looked much like an exclamation mark, but is not. So in red, it is what you expected to get in the condition, checking the environment with the constant. But in fact, what the code was doing was affecting the constant value to the environment with the retroflex click character in the variable name. So the affectation will always be true. So in the code, it will always lead to return true and get a bypass of the authentication mechanism. So it could be a way to introduce backdoor in a source code. Similarly, there are a lot of invisible characters like control characters, spacing, filers, etc. that can also be used to put some backdoor in source code. So, for example, on the left, you can see in the JavaScript console, I affected the alert function into an invisible variable. The yes value string is affected to the yai variable. And what you expect when I check if the yai variable is strictly equal to no, it's for the condition to be false. But as you can see on the right, I used the harmful filer, which is an invisible character, and I put it between the equals and the no string. So instead, it will evaluate this variable and do alert no. So I could execute some code where visually you don't expect any code evaluation. So as we just saw, invisible characters can lead to source code backdooring. In many other examples we won't see there, but for example, there are attacks where you introduce some backdoor code into a comment, it visually looks like the malicious code is in the comment, but in fact is outside the comment. A big issue we'll have with Unicode is the size. So when you think about encodings, you are always thinking about ASCII and how it was very easy, because when you have one character in ASCII, you have visually one character. It will be encoded as 1 byte. It is always one ASCII unit, so the size is always 1. It's quite easy. But if I show you this emoji, what is its size? And when I ask you what is the size of what? In fact, this emoji is a join one, so you have 6 Unicode code units, so 6 Unicode code points. First, you will have the woman emoji, then you'll have a joiner character, then you will have the heart emoji, then you will have a color variation selector for the heart to be red, another joiner, and then the man emoji. So you have 6 code units. But visually, you have only one character. So what you saw is called a graphem. So that's what a human can see. So there is only one graphem. But as we saw, there are 6 code units. And depending on the Unicode encoding you choose, the size will be different. So maybe 20 bytes in UTF-8, 16 in UTF-16, and 24 in UTF-32. So in this Node.js or JavaScript code, so you know JavaScript is using UTF-16. If you use naively the default len function, it will return 8. So it's none of the size we saw earlier. Why is that? I didn't introduce how UTF-16 is working, but there are quite short characters and long ones. And for example, the first and the last emoji are longer ones, so they are split into 2 surrogates. So UTF-16, in UTF-16, it makes like 8 units instead of 6. It doesn't make sense. It's not useful at all. But Node.js will return that. If you want to get the correct code unit, you have to use on the second line that weird array splitter syntax. And as you can see a few lines below, UTF-16 size should be always the same, but if you ask for the byte length in low Indian or in big Indian, you will get different results. I don't have an explanation for that. It's quite weird. And on the last line, if you want the graphem size, you have to use this quite complex and counterintuitive syntax that is maybe not well documented. But hopefully on other languages, like, for example, Ruby, you have native methods that are much easier and intuitive to use. So these size issues, if the developer is using the wrong values, could lead to, for example, depending on the language, buffer overflows or string truncation. Of course, if you are using the wrong size as an index, you won't go where you expect it to, and so you can misplace, for example, some sanitization. Well-known and interesting use case is the case transformation for strings. So, for example, when you lowercase or uppercase or apply some transformation to strings, in ASCII, it was quite easy because when you have for example, lowercase a, and uppercase it, you will always get the uppercase A, and no other character will lead to an uppercase A when you uppercase it. But in Unicode, you have, as I said earlier, around 4 million characters, and many mechanisms, so it's much more complex. For example, when you uppercase or lowercase a character, it could transform into several ones, and as such, when you have several characters, they can lead to only one. Also, there will be transformations that will depend on the context, so if another character is behind or right after. And also, it could also depend on the regional setting. I will give some example right after this slide. But it can lead to changing the string length and creating collision. We will show some attacks based on that after, entry mismatch, and all kind of security bypass. A well-known case, for example, of uppercase collision is with this, I think it's a German character that looks a bit like a B. So when you uppercase it, it will transform into two uppercase S. So in input, we have only one character, and on the output, we have two of them. So it will transform the string length. The other way around, for example, we have this Kelvin sign for temperature. Then when you convert it to lowercase, it will give a normal lowercase k. So it means to get a lowercase k, you can have several different inputs. For example, the uppercase k will give a lowercase k, but also the Kelvin sign. So you could claim some collision. We'll see an attack after that. And for the contextual transformation, it's not much interesting, but for example, you can see it's mainly with Greek characters. Depending on what you placed before or after, it will get a different output. And also with regional settings, as you can see, if I use some French local and I lowercase an uppercase A, I will get a normal lowercase high. But if I do the same with the Azeri local, I will get a dotless I, which is not the same character. So the output will depend on what is your local. Right now, I will give you an example of account takeover via password reset using this lowercase transformation collision. So if you quickly read the source code, it's an API that is doing some password reset. So there is, as an input, the email address that the user can control. It is lowercase and used in a prepare statement in a SQL query, so kind of to normalize and be able to always compare the same value in the database. We'll get the ID of the user, and then the application will generate a temporary password or reset link or whatever, and send it to the user. In case of a legitimate user, you know, the lowercase it just used as normalization. It's bad, but it's what's done here. For example, if there is some uppercase in the address, it will transform to lowercase to be able to compare with what the database is storing. But if we took back the Kelvin sign I showed earlier, as you remember, it will collision with a small letter k when transformed to lowercase. So if you took this address and on the left, on the synactive.com domain, instead of a k, I put the Kelvin sign, but when lowercase, it will also result in a synactive with a small k in it. So what will actually happen is that On the SQL query, the user input is lowercase. So we'll get the legitimate administrator address. So we'll also get its password reset token. But when the email will be sent, the email input is not lowercase, so it will instead be sent to the synactive with a Kelvin sign domain, which is a entirely different domain. So it will result into sending the password to the hacker. I wrote a similar article in the string functions in MySQL and MariaDB that you can read in the free page.out magazine. So now let's talk about normalization. What you should maybe use instead of lowercase when you try to normalize something. There are actually 4 different types of normalization in Unicode. So the first one is NFD. It will try to decompose complex character into multiple ones. The NFC will do the same, but will try to recompose them after that. The NFKD and NFKC are the same as NFD and NFC, but are kind of a compatibility mode. So when decomposing, they will use, let's say, simpler and shorter characters. So on the last line, you saw that depending on the normalization, you will get different output for the same character. I will give you 2 examples of attacks using normalization. One is host splitting, and the second will be XSS filter bypass. So I think the first occurrence, the first time we heard about the host splitting vulnerability was at the Black Hat in 2019. And it's an attack that is about abusing the normalization compatibility mode to bypass URL whitelist. So if you take this character, which is called addressed to the subject, when you normalize it with one of the 2 compatibility mode normalization form, like NFKD and NFKC, it will result in 3 separate characters, a slash, and an S. So if you have a domain like on the first line, so synactive.somewherestuff.target.com, you have actually a subdomain of target.com that will pass the test if there is a whitelist with, for example, wildcard.target.com. But if in the code it's normalized using NFKD or NFKC, as you can see in the comment, it will result into synactive.ca/support.target.com. So support.target.com actually became just a path. So the URL will lead to an entirely different domain. In this example, I used the .ca TLD, but I could have used any TLD that ends with an A. There are other, what I call splitters character like that. So, for example, the 2 last one, you will be able to use a TLD that ends with a C. But there are much more characters that, when normalized like this, will also result into interesting characters to manipulate URLs. So, for example, that will result into a question mark that will be interesting to play with get parameters in HTTP queries. That will result into a slash. So it's the same as the example we saw, but here you won't have any constraint on the TLD. And other stuff like getting an anchor or an @sign to play with, for example, with usernames. Also 2 dot to get some to generate some credential, and maybe an interesting one to bypass, for example, a filter that will check that you use a domain name and not an IP address. There are characters like when normalized will transform into numbers followed by a dot. So you can use them to craft IP address and get a valid domain that will be transformed into an IP address. This attack can, for example, be used to bypass URL parsers, but also often used to bypass, for example, when you have whitelist based on regular expressions. And let's say you have a web server or maybe a web browser that is taking as an input a location header and will normalize it. It could then result into redirecting to a different domain. So the second attack I'll talk about is how to bypass some XSS filters using normalization. I will show two examples. So normally, developers use a function like to escape HTML entities. So HTML special character will be in an escape form, but there are actually some weird Unicode characters that, when transformed with NFKC or NFKD, will result into a normal opening or closing HTML tag. And the same for quotes and other HTML special characters. So this is just a few lines of code to prove it. So normally, if you use in a secure code, if you will get an XSS payload, it will the result will be escaped, so your XSS won't trigger. But on the first line, if I use some Unicode characters to replace the opening and closing HTML tags, apply some escaping, nothing will happen because that's some Unicode characters, no HTML sequences. So if it's inserted like that in the code, nothing will be executed because it's not valid HTML. But if later on the code, the NFKC or NFKD normalization form is applied, then this Unicode special character will be transformed back into the opening and closing HTML tags. So you will get your XSS and have successfully bypassed the escaping mechanism. Here, the issue we'll see later is due to the incorrect ordering of the filtering steps. They should have been done the other way around. But you can also come to such an issue because there are a lot of normalization that is happening in framework or databases, and you don't even know that it's applied. So what I was saying is that it was because of the ordering of the sanitizing, because if you have these Unicode sequences, apply the escape HTML, nothing will be escaped because there is no HTML entities in them. And if then you normalize, you will get back the HTML entities, like mutated XSS. So instead, you should have done it the other way around, because if you first normalize it, you will get the HTML entity, and then when you will apply the escape HTML function, they will be effectively escaped. And what does happen when you don't have a compatibility mode normalization, for example, like NFC? NFC is interesting because despite not doing some compatibility mode, it will try to recompose what was first decomposed. So if I I get a normal closing HTML character followed by a word Unicode character. It will result, as I tell you earlier, that there is some composing mechanism that could combine two characters into one. So it's what will happen here, and recompose this into another Unicode character, but that have no meaning in HTML. So what will happen here, and this is my last example, it's if you have an injection on, for example, text area HTML tag with some attributes, there is a closing HTML tag and then your injection. So if you inject this Unicode character and then the rest of your payload, here nothing will be escape if there is an HTML escape sequence, because there is no HTML special characters in it. But if after that an NFC normalization is applied, so the closing HTML tag with the Unicode character following it will be recomposed into another stuff that will be part of the value of the ID attribute. So then your whole payload will be into the attribute of the tag. So it will result in an XSS. And thank you, everyone. It was my last example. I hope you learn a lot. Thank you.